Well, I'm a mathematician and I like YouTube, and I'm often inspired by stuff that I see on YouTube. And recently I saw 2 clips that gave me an idea. I just want to tell you about those. Impressive. I'm sure they don't do anything else but march. That's their main occupation, right? Now this is impressive, but what I found even more impressive was some Japanese people competing in a marching competition. So here we go. Now that's really impressive. Anyway, so I had this idea, well, there's basically squares marching around. Obviously, as a mathematician, I like squares, I like circles, these sorts of things. So I thought, well, maybe what I want to do is, or I had this idea, was you've got 2 squares kind of marching around, and what I wanted to do is kind of devise some sort of choreography for these 2 squares merging into one big huge square. Right? So you can imagine the 2 squares kind of marching around there, and then eventually they kind of come together and whoops, you see like one big square marching, okay? Well, that's a good idea, so let's just see whether we can do this, okay? First thing we have to figure out is how big do we want to make our squares, okay? So we could start with really, really small ones like, so tawatus, right? Is that going to work? Let's have a look, right? So we've got 4 marches in here, another 4 marches in there. That's a total of 8 marches. But we need a square number of marches, right? So that's not going to work, right? So we can't really go really small. What about the next size up? 3 times 3 and 3 times 3. So that's 9 here, and it's 9 there. That's together 18. Again, it's not a square number, so it's not going to work. Okay, let's keep on going. 16, 16, that's 32, not a square number. Okay, then 25 plus 25, that's 50. Well, it's actually pretty close. 49, so it's just 1 off. So. Well, anyway, let's keep searching, right? So eventually we're going to find something, hopefully. We're already pretty close here, right? Let's use this. It's actually not going to work, but eventually it's going to work. And I just want something small. It's a near miss, right? So this is 12 squared, this is 12 squared. So 12 squared is 144 times 2 is 288. And that's 17 squared, it's 289. So it's also just 1 off, right? And it's good enough to actually show us what's going to happen, okay? So now, let's not worry about actually finding the right example. Let's just keep on going with our choreography. How we're going to actually merge those 2 squares together, okay? And also the other thing that I want to say, I'm probably, since I have so much trouble kind of finding these squares, I'm going to use the smallest example eventually. It's going to be important for later on, okay? So this, let's just say this is the smallest example that exists, okay? And so now we're going to do our choreography. We're going to merge those 2 squares together. So here we go. So we're going to march these squares around, okay? And these are actually the guys who are marching, and this is kind of just a template for us to see where they now actually have to go, right? Eventually these blue dots have to fit into this grid here. Okay, so what we're going to do is just march these 2 squares in from the left and the right, okay, like that. And they're going to overlap here in the middle. It's a bit of a problem maybe, but not really. You just have some marchers stand on their comrades' shoulders, right? So here we're basically all doubled up. Where the red points are, that's all doubled up, right? Okay, so what that means is, in the square that we're seeing here, there's nobody standing here. There's just 1 person standing in the blue bits, and on every one of the red bits, there's 2 people doubled up, right? So if I just take the guys who are standing on the shoulders, they should now fit into those empty squares, right? Because eventually, you know, whatever we had to start with is supposed to fill in all the gray spots, right? So what that means, of course, is that this red square is exactly as big as those two little ones combined together, right? So that's a logical conclusion, right? So this one plus that one equals that one. Okay, well, that's great, but there's something really, really, really strange here. Remember, we started out with saying this is the smallest example where two smaller squares combine into a larger square. But now we found an even smaller one. How is that possible? That's supposed to be the smallest example, and now we found an even smaller one. Well, you can think about it, but actually the only way you can resolve this paradox is to say, well, there is no smallest example. Because if there's a smallest example, there can't be any smaller example. Right? So we basically started with an assumption that we can find the smallest example, but basically that shows us, this kind of paradox, this contradiction shows us there can't be a smallest example. So there is actually no way to merge two squares into a larger square. So that's what we just shown. That's actually, in mathematics, it's called a proof by contradiction. You kind of assume that something is the case, okay? And then you make logical deductions until you come to a point where you can see there's some nonsense here. But from something that's true, nonsense can't follow. So that means that what you started with has to be nonsense in the first place, and that means that whatever else is the opposite of what you assumed has to be true. In this case, two squares cannot possibly combine into a larger square. All right. So we can also express this like mathematically or algebraically. You can say that two integer squares can't add up to another integer square like that. And then we can transform this a little bit. So 2 times m squared is equal to n squared doesn't work. And then if you divide here, that one can't work. And now if you do a square root, you see, that one can't work. And what that says here is that the square root of 2 cannot be written as a fraction of integers. And what that says is that square root of 2 is irrational. So actually our marching square scenario, our marching square consideration also show that the square root of 2 is irrational. All right, now what else can we say here? Okay, this was actually the near-miss example that I used, okay? This near-miss example that I used. So it was 12 squared plus 12 squared equals 17 squared minus 1. Well, I mean, I just used this for illustration, but actually, when you really do it, and I'm just going to do it again in a nice symmetric way, there's something nice coming out of this, and I just want to show you that one. Okay, so you just kind of march these squares in now this way, and then we get the same overlap as before, right? Okay, and then actually, because we started out with a near miss, I mean, if this was exact, then the green bit should be exactly as big as these two combined together. But since we started with a near miss, well, we should be close again, right? We should be close again. We can actually check now. We've got 1, 2, 3, 4, 5. And here we've got 1, 2, 3, 4, 5, 6, 7. That's the other near miss that we kind of encountered already at the very, very beginning. That's 5 squared plus 5 squared equals 7 squared plus 1. Okay? And why stop there, right? So we can just move those two guys into the middle now, and they're going to create an overlap. And let's just see what we get here. Well, we've got 2 squared. There we go, 2 squared. That's 8. And just off by 1 from 9. So that's another near miss here, right? So we get another near miss there. And, well, what else? We don't have to stop there, right? So we've got a, well, it's a really simple one, but it's still a near miss. 1 squared plus 1 squared equals 1 squared plus 1. Okay. Right, so with one of those near misses, we kind of get all sorts of other near misses when we kind of repeat this merging procedure. It's really, really quite fun. And actually we get all of the smaller ones. But we can also kind of go backwards. And when we go backwards from here, we actually get all the near misses that they are. Okay? So let's just go backwards. So kind of go like this. So unmerge, right? Then we put the square around. Unmerge. It gets us back to the beginning. Now, if we want the next higher or the next bigger near miss, what we do is we just put a big square around this, like so. Measure how wide this is, right? And then there's another square inside. Measure how far this is, and we get 29 squared plus 29 squared equals 41 squared plus 1. And then we take those two squares, again arrange them like this, put a big square around it, and we get another example and another example and another example. And that's actually going to be all examples of two squares adding up to another square with a difference of just 1. Okay, and we can, there's a couple of this is the 4 examples that we actually had a look at here. There's more, right? There's heaps more here on the left side. And well, those near misses, they are also really nice in another way. So that, for example, was 1, 1, 3, 2, 7, 5. If you just actually look at them as fractions, you get a 1 here, you get a 1.5 there, you get a 7, you get a 1.4 there, and that one here. And what do you think is happening here? Well, they're getting closer and closer to square root of 2. Right? And especially this one, these are actually really, really nice approximations, really, really good approximations to square root of 2. So I mean, people always obsess about pi, and like one of the things you know about pi is that 22 over 7 is almost pi, right? So if you're actually looking for a fraction that does the same for square root of 2, you'd probably go for this one here. Nobody knows this one, but 17 over 12 plays the same role for square root of 2 as 22 over 7 plays for pi.